Tonight, the most famous dying star in the sky just got a lot more complicated. For decades, astronomers told us Betelgeuse had roughly 100,000 years left. Comfortable, distant, not our problem. That estimate quietly collapsed in the peer-reviewed literature over the last 18 months, and almost nobody outside professional astronomy noticed. There is a hidden companion named Siwaha plunging through the star's own atmosphere. A January 2026 Hubble result just physically detected its wake, and the remaining lifetime has shifted from 100,000 years to something the literature describes as uncertain by orders of magnitude, which is the careful, professional way of saying we genuinely do not know anymore. Here is the part that should stop you cold. The light hitting your eye right now left Betelgeuse in 1386. You are not watching a live feed. You're watching a 600-year-old recording of a star that may have already changed in ways no telescope on Earth can see yet. The present state of Betelgeuse is, in the most literal physical sense, invisible to us. So what is actually happening up there? What did the Hubble result really find? Why did the textbook story collapse so quietly? And when the alert eventually fires, and there will be an alert, what do the next 24 hours actually look like for the rest of us? Get comfortable. Hit subscribe if you have not already. We're going all the way through this one, and I promise, by the end, the way you look up at Orion will never be quite the same. Part 1. The timeline didn't shorten. It disintegrated. The textbook is wrong, not outdated, not slightly off, not in need of a minor correction, wrong in a way that changes everything we thought we knew about the most watched star in the night sky. And the strangest part is that almost nobody outside a handful of university astronomy departments has noticed yet. For decades, if you asked anyone with a telescope and a basic knowledge of stellar physics about Betelgeuse, they would have told you the same thing. Stable. Aging? Yes. Massive, certainly. Destined to explode? Absolutely. But not soon. The standard answer, the one that appeared in textbooks, in science documentaries, in countless articles, was that Betelgeuse had roughly 100,000 years remaining before it would end its life in a core-collapse supernova. 100,000 years. That number was stated with the quiet confidence that comes from decades of consensus. It felt safe. It felt distant. It felt like something your great-great-grandchildren to the power of about 500 would have to worry about. So we watched the star, we appreciated it, and we moved on with our lives. That estimate is no longer reliable. And the way it collapsed, not through a dramatic announcement, not through a headline-grabbing press conference, but through a slow accumulation of peer-reviewed papers published between 2024 and 2026, is itself one of the most remarkable stories in recent astronomy. The model didn't collapse loudly. It dissolved quietly, paper by paper, inference by inference, until the floor of certainty was simply no longer there. To understand why this matters, you need to understand what that 100,000-year figure actually represented. It was not a measurement. You cannot point a telescope at a star and read its remaining lifespan off some cosmic odometer. What astronomers did was build a model. They took what they knew about Betelgeuse, its mass, its luminosity, its temperature, its spectral type, and they fed those parameters into stellar evolution equations that have been refined over the better part of a century. Those equations describe how stars burn through their nuclear fuel, how they expand and contract, how their cores evolve through successive burning stages, and ultimately how they reach the threshold conditions that trigger collapse. The 100,000-year figure was the output of that model, and the model, it turns out, was built on an assumption so fundamental that nobody questioned it. The assumption that Betelgeuse was alone. It was not alone. There is something else out there, something close. Dangerously, impossibly close, and the discovery of that companion, or more precisely the realization that evidence for it had been hiding in the data for decades, is what triggered the cascade of reinterpretations that has now fundamentally destabilized everything we thought we knew about this star. The shift happened through 3 separate lines of evidence, each arriving from a different direction, each individually interesting, and together collectively devastating to the old model. The first came from the work of MacLeod and colleagues, who reanalyzed the long-period oscillations that had been observed in Betelgeuse's brightness and velocity data for years. Astronomers had always known that Betelgeuse wobbled. Its brightness varied on a cycle of roughly 420 days, which was attributed to pulsation, the star breathing in and out. But overlaid on that was a longer, slower cycle of about 5.78 years that had never been fully explained. Some papers called it the long secondary period. Others called it noise. Nobody called it what it actually appears to be, an orbit. McLeod's team ran the numbers on radial velocity measurements and astrometric data, and the convergence was uncomfortable in the best possible scientific way. The 5.78-year period was not a pulsation mode. It was not a convective artifact. It matched, with a precision that was difficult to dismiss, the signature of a companion object moving around, or more accurately through, Betelgeuse's outer atmosphere on an orbit with a period of approximately 2,110 days. The separation between the two objects was estimated at roughly 2.3 stellar radii. To put that in context, imagine a planet orbiting so close to the Sun that it was skimming through the outer corona. Now imagine that instead of the Sun, the central object is a star so large that if it replaced our own Sun, its surface would extend past the orbit of Jupiter. The companion is not somewhere out in space. It is inside the star's extended envelope. It is inside. The second line of evidence came from imaging. Howell and colleagues published results using the most capable ground-based and space-based imaging systems available, attempting to resolve the Betelgeuse system directly. The results were tantalizing without being definitive. The companion is not cleanly separated from its host. It is embedded in what is essentially stellar atmosphere, surrounded by gas and plasma and magnetic fields, all of which conspire to blur and scatter any signal that tries to get out. But the asymmetries in the extended emission around Betelgeuse, the way certain parts of the outer envelope are brighter, denser, more disturbed than others, are consistent with the presence of an object ploughing through the gas and leaving a structured wake behind it. You can see the footprints even if you cannot see the foot. The third line, and in many ways the most decisive, arrived in January of 2026, when a team analysing approximately 8 years of ultraviolet monitoring data from the Hubble Space Telescope published their findings. Hubble had been watching Betelgeuse in the ultraviolet for reasons that had nothing to do with a companion search. UV observations are used to probe the chromosphere and understand mass loss. But when the team processed 8 years of that data and looked at the phase relationships between the absorption features they were seeing and the orbital period predicted by McLeod's work, something clicked into place. The absorption lines in manganese, iron and magnesium, traces of material moving through the chromosphere, were not varying randomly. They were varying in a pattern that was locked to the orbital phase of the supposed companion. The outflows were stronger, the velocity structure more complex at specific points in the 5.78-year cycle. Not sometimes, consistently, for 8 years. This is what phase locking means in practice. It means that whatever is driving the perturbation in Betelgeuse's outer atmosphere is not a random internal process. It is tied to something external, something moving on a repeatable trajectory, something with a period. And the period matches. The implication is not subtle. The companion is physically interacting with Betelgeuse's chromosphere on every pass, dragging material outward, compressing gas, seeding outflows. The star is not just being observed from a distance, it is being modified repeatedly and measurably by something inside it. Now, here is why all of this destroys the timeline. Stellar evolution models, the ones that produce the 100,000-year estimate, are built on assumptions about how mass leaves a star. A red supergiant like Betelgeuse loses mass continuously through stellar winds, and the rate at which it loses that mass is one of the critical parameters that determines when it will die. Lose mass too slowly, and the core builds up pressure and temperature on a certain schedule. Lose mass faster, and the schedule compresses. The models that gave us 100,000 years assumed a smooth, spherically symmetric single-star mass loss rate. No companion to stir the pot. No orbital perturbations to drive periodic outflows. No structured wake carving through the envelope and ejecting material in preferential directions. Once you introduce a companion that is actively inside the envelope, doing measurable things to the chromosphere on a 5.78-year cycle, those assumptions are no longer valid. The mass loss rate is not what the models assumed. How different is it? That is the uncomfortable question. And the honest answer, the one that several papers in the last 18 months have been circling without quite landing on directly, is we do not know, not within a factor of 2. not within an order of magnitude. The uncertainty is not a small error bar on a confident number. The uncertainty is the number. There is something almost philosophically disorienting about this. We spent decades looking at Betelgeuse and thinking we understood it, because the math worked out to a comfortable answer. 100,000 years. That is a long time. Nobody alive today needs to think too hard about it. But the math worked out to that answer because we fed it incomplete information. We were solving the right equations for the wrong system. And now that we know, or strongly suspect, that the system is not a single star but an interacting binary, the equations are still the same but the parameters have changed, and the output is no longer a comfortable number. The output is a shrug and an error bar large enough to swallow geological epochs. The public largely still believes the old story. If you asked 100 educated people tonight what they know about Betelgeuse, the majority would say something like it's a red giant that will explode eventually but not for a very long time. That is the story that propagated through a generation of science communication, and it is not wrong in the way that a provably false statement is wrong. It is wrong in the way that a map drawn before a major earthquake is wrong. It was accurate when it was made, but the ground has shifted and the map no longer reflects the territory. The peer-reviewed literature has already moved on. The papers are already published. The recalibration is already happening. The public just hasn't been told yet. And the reason the public hasn't been told is partly that the science is still unfolding. There are papers in review right now that will sharpen or revise these conclusions, but also partly because the conclusions are genuinely uncomfortable. Saying, "We don't know when Betelgeuse will explode and the uncertainty spans orders of magnitude," is not a satisfying headline. It doesn't have the clean drama of a countdown. But it is, as best as we can tell right now, the truth. The timeline didn't shorten, it disintegrated. And what replaced it is something far more unsettling. A system whose internal physics we do not fully understand, driven by a companion we cannot directly see, monitored through light that left the star before the printing press was invented. Which brings us to the question that should be sitting in the back of your mind right now. If the companion is inside the envelope, interacting with the chromosphere, driving structured mass loss on a measurable cycle, what is it actually doing to the star? What does a close companion plunging through a red supergiant's outer layers actually look like from a physics perspective? And is there any chance that what we saw in 2019 and 2020, that dramatic, mysterious dimming event that made front pages around the world, was not just an interesting coincidence, but the first visible sign of exactly this kind of orbital perturbation? Chapter 1. Part 2. The companion that shouldn't be there. Steglin. There is a specific quality to anomalies that refuse to go away. In science, when you see something strange in your data, the first instinct is to explain it as error, instrument noise, calibration problems, a bad night of seeing, a statistical fluctuation that happened to look meaningful. The second instinct is to find the simplest possible physical explanation that fits within existing models. It is only when both of those fail, and the anomaly persists across independent datasets collected with different instruments by different teams over different years, that you start to seriously consider the possibility that the anomaly is not a mistake. It is real, and it is telling you something your model cannot accommodate. The long secondary period in Betelgeuse is exactly this kind of anomaly. Astronomers have known for decades that Betelgeuse's brightness does not vary on a single clean period. The dominant pulsation cycle runs somewhere around 420 days. The star literally expands and contracts, brightening as it swells and dimming slightly as it contracts, in a cycle that has been observed consistently for over a century of photometric data. That is normal for a red supergiant. It is expected. But running underneath that pulsation cycle, quieter and slower and harder to pick out, is a second signal with a period of roughly 2,110 days, approximately 5.78 years. This is the long secondary period, and for most of the history of Betelgeuse research, it was treated as an annoyance more than a discovery, something to account for in the data reduction, something to filter out, an artifact of complex internal dynamics that didn't fit neatly into any model but wasn't dramatic enough to demand a revolution. The name given to the proposed companion is Siwaha. The name comes from an Ojibwe word, part of the broader effort within astronomy to give celestial objects names that reflect indigenous knowledge and language traditions. a recognition that these stars were observed, named, and woven into navigational and cultural frameworks by cultures around the world long before European astronomical institutions put them in catalogues. Siwaha. It sounds right for something that has been there all along, hiding in plain sight, waiting for us to stop misidentifying it. The orbital parameters that McLeod and colleagues derive from the radial velocity and astrometric data are what make this system so extraordinary. An orbital period of 2,110 days, a separation of approximately 2.3 stellar radii. Let those numbers sit for a moment, because they require translation to make sense at the scale of what we are actually talking about. Betelgeuse is approximately 700 times the radius of our own Sun. 700 times! If you put Betelgeuse where our Sun is, its surface would extend past the orbit of Jupiter, the largest planet in our solar system, and probably past the orbit of Saturn as well, depending on which measurement you use. The photosphere alone, the visible surface of the star, is a sphere of superheated plasma larger than our entire inner solar system. And Siwada is orbiting at a distance of 2.3 times that radius. 2.3 stellar radii means the companion is not in some comfortable middle distance. It is grazing the outer edge of what we would, in any normal astronomical context, call the star itself. But here is where the physical picture gets even stranger, because red supergiants are not simple objects with clear-cut boundaries. A main sequence star like our Sun has a photosphere that transitions fairly sharply into a thin atmosphere. A red supergiant like Betelgeuse is a different beast entirely. Its photosphere is the innermost layer, the surface that radiates the light we see. Above that is a chromosphere, a zone of hotter, lower density plasma extending further out, threaded with magnetic fields and shock waves driven by the pulsation below. Above the chromosphere is an extended envelope, a region of gas and dust and complex chemistry that extends many stellar radii further still, gradually thinning out until it becomes indistinguishable from the interstellar medium. When you hear that Betelgeuse is surrounded by multiple shells of ejected material, those shells were created by mass loss events over thousands of years of stellar evolution, and they exist in this extended region beyond the chromosphere. Siwaha, based on the orbital parameters, is moving through the chromosphere, not orbiting outside the chromosphere, not orbiting above the extended envelope at a safe distance, moving through the region of active plasma, magnetic activity, and outflowing material that we call the chromosphere. Every 5.78 years it completes one orbit. Every 5.78 years it passes through the same general region of Betelgeuse's outer atmosphere, compresses the gas it encounters, transfers momentum to the surrounding plasma, and perturbs the convective and magnetic structures it intersects. The physical consequences of this are not subtle, but they are complex. When an object moves through a gaseous medium, it does not pass through cleanly. It creates a bow shock on its leading edge, where compressed gas piles up. Behind it, the gas rushes back in to fill the void, creating a turbulent wake of eddies and density variations. In a normal astronomical context, a planet orbiting through a thin stellar wind, for example, these effects are negligible. The object is much smaller than the medium it is moving through, and the medium is thin enough that the perturbation dissipates quickly. But Siwaha is not moving through a thin stellar wind. It is moving through the chromosphere of a supergiant, a region of plasma that is orders of magnitude denser than a stellar wind, and orders of magnitude more energetically active. The perturbation does not dissipate quickly. It structures the gas, it creates preferential pathways for material to leave the star. It couples the angular momentum of the orbit to the rotation of the stellar envelope. This last point is particularly interesting, because Betelgeuse has long been known to rotate faster than expected. A red supergiant at this stage of its evolution should be spinning slowly. It has expanded so dramatically from its original main sequence size that conservation of angular momentum dictates it should have slowed to a near crawl. But Betelgeuse is spinning faster than that. Various measurements over the years have produced different numbers, but the consensus is that the rotation is anomalously rapid for a star of this type and age. For a long time, this was another unexplained anomaly. Now there is a candidate explanation: tidal coupling. If Siwaha is orbiting inside the extended atmosphere, the gravitational interaction between the companion and the rotating envelope can transfer angular momentum from the orbit to the envelope, effectively spinning up the star's outer layers. The companion is not just perturbing the gas, it may be dragging the entire chromosphere around with it. Now, it is critical to be honest about what is and is not established here. Siwara has not been directly resolved by any telescope as a distinct point source, cleanly separated from Betelgeuse. The evidence for the companion is convergent but indirect. It comes from the pattern of radial velocity variations, from the astrometric wobble in the star's position over time, from the phase-locked behavior of the UV absorption features, and from the structural asymmetries visible in high-resolution imaging of the extended envelope. Each of these lines of evidence is consistent with a companion at the derived orbital parameters. None of them is definitive on its own. Several of the papers discussing Siwara are careful to use language like consistent with, best explained by, and strongly suggestive of. This is not waffling. This is the appropriate epistemic humility of scientists who know that the data is pointing strongly in one direction, but also know that extraordinary claims require extraordinary evidence, and direct imaging of the companion itself would significantly strengthen the case. That said, the convergence of evidence is genuinely striking. You have a multi-decadal anomaly in brightness data. You have radial velocity variations that match an orbital period. You have astrometric signals that match an orbital solution. You have ultraviolet observations that show phase-locked behavior over 8 consecutive years. These are not all the same data set dressed up in different ways. They are independent observations made with different instruments using different physical principles, and they are all pointing at the same conclusion. At some point, Occam's razor becomes decisive. The simplest explanation for all of these observations simultaneously is a companion in a close orbit, and the properties of that orbit, period, separation, eccentricity, are constrained well enough to say something meaningful about what that companion is doing inside the star. What it is doing is not orbiting peacefully. It is not a distant observer. It is an active participant in the physics of the system, perturbing the chromosphere, coupling to the magnetic structures, seeding outflows, and potentially modifying the mass loss rate in ways that the standard stellar evolution models never accounted for. Betelgeuse has been running this interaction for as long as it has had a close companion, which, if the companion formed with the system, or was captured early in its evolution, could mean millions of years. The system we are observing tonight is not the same as the single-star Betelgeuse that our models describe. It never was. We just didn't know to look for the difference. And this brings us back to the central problem. If the mass loss rate is being modified by the companion in ways we do not fully understand, then the remaining lifetime estimate, already uncertain by the nature of stellar evolution calculations, gains an additional unquantifiable layer of uncertainty. The star's mass, which determines everything about the timing of core collapse, is not well constrained if we do not know how much mass the companion is pulling out of the envelope on each orbit. The core evolution depends on the envelope. The envelope is being disturbed. The model is compromised. Not broken beyond repair, but broken enough that the comfortable 100,000-year answer is no longer available. But if you are thinking that this companion interaction is interesting in a purely theoretical way, that it is a fascinating orbital mechanics puzzle with no immediate dramatic consequences, I need you to hold that thought, because there is one more piece of evidence, one more observation published at the beginning of 2026, that does not just support the companion hypothesis, but physically demonstrates that the interaction is happening right now, in real time. Well, in real time adjusted for the 620-odd light-years of delay, and that the consequences for Betelgeuse's outer atmosphere are not subtle at all. Chatouillia. Part 3. The 2026 Detection That Changes Everything. Jacques. 8 years is a long time to watch anything. It is long enough for a child to go from kindergarten to middle school. It is long enough for a nation to go through 2 complete election cycles. It is long enough for a star in a 5.78-year orbit to complete more than 1 full revolution around its companion. And it is exactly how long the Hubble Space Telescope team spent monitoring Betelgeuse in the ultraviolet before they published the result that, in January of 2026, transformed the companion hypothesis from a compelling inference into something much closer to a demonstrated physical reality. Ultraviolet astronomy is not the kind of thing that tends to generate public excitement, which is a shame, because the ultraviolet is where some of the most important things in stellar physics happen. Human eyes are tuned to a narrow window of the electromagnetic spectrum, the range we call visible light, spanning roughly from 400 to 700 nanometers in wavelength. Stars emit across a far broader range than this. Red supergiants like Betelgeuse are cool by stellar standards. Their photospheres hover around 3000 to 3500 Kelvin, which means their peak emission is in the infrared and red optical. But the chromosphere above the photosphere, despite being in some ways a thin and tenuous structure, is heated to much higher temperatures by shock waves and magnetic processes, and hot plasma radiates in the ultraviolet. Monitor Betelgeuse in the UV, and you are not seeing the star's surface. You are seeing the chromosphere, the active, dynamic outer layer where mass loss originates and where a close companion would do its most direct and observable damage. The specific signatures the team was tracking were absorption lines from 3 elements: manganese, iron, and magnesium. These are not exotic choices. In stellar spectroscopy, these elements are workhorses. Their absorption lines are well characterized, their formation conditions are understood, and their velocity structure tells you something meaningful about the motions of the gas absorbing the star's light. When you see a manganese absorption line shifted to shorter wavelengths, blue shifted, in the language of spectroscopy, it means the manganese gas is moving toward you. Since we are looking at Betelgeuse, gas moving toward us is gas moving away from the star's surface. It is outflowing material. The blue shift of these lines is essentially a direct measurement of how fast material is leaving Betelgeuse's chromosphere at any given moment. What the team found, after processing 8 years of these measurements and folding them against the orbital phase of the predicted companion, was a pattern that should not exist if Betelgeuse is a single star. The outflow velocities, the speeds at which chromospheric material was being ejected, were not random. They varied on the 5.78-year cycle. Specifically, they increased in the orbital phase windows corresponding to when Siwaha would be moving through the densest parts of the chromosphere based on the orbital solution derived by McLeod's team. After the orbital phase window corresponding to companion transit, the UV absorption features showed enhanced outflows, stronger signals, faster velocities, more material in motion, phase-locked. The word is important. Phase locking is not correlation in the casual sense. It is not the kind of thing that happens by accident in a dataset with multiple overlapping signals. Phase locking means that the variation you're seeing is repeatable, predictable, and tied to a specific causal mechanism on a specific period. For this to show up consistently over 8 years of independent UV observations, covering more than one complete orbital cycle of the companion, requires an explanation that invokes something real, something physical, something that recurs on exactly that period. And the only mechanism on the table that operates on the 5.78-year period is Siwaha. The team used the word wake to describe what they were observing, and it is worth spending a moment on what that actually means physically. A wake, in the everyday sense, is the disturbed water behind a boat, the V-shaped pattern of waves that propagates outward from a moving object and persists for some time after the object has passed. In the context of a companion moving through stellar atmosphere, the wake is a zone of enhanced density, elevated temperature, and structured velocity gradients that forms in the gas through which the companion has recently passed. Betelgeuse's chromosphere, like all chromospheres, is not a smooth, uniform medium. It has convective flows, magnetic field structures, density gradients, and shock fronts moving through it from the pulsation below. The companion's passage through this medium does not create a clean, boat-wake-like structure. It creates something more complex, a zone of perturbed gas that interacts with all of the pre-existing structures, amplifying some motions, disrupting others, and ultimately creating a net outward flow of material that was not going to leave the star on its own timeline. The physical mechanism here is essentially tidal and aerodynamic. As Siwaha moves through the chromospheric gas, it exerts a gravitational pull on the surrounding material. Gas on the near side of the companion, between Siwaha and the photosphere below, is attracted upward. Gas ahead of the companion in its orbital path is compressed into a bow shock. Gas in the companion's wake is dragged along behind it, creating a channel of enhanced outflow. The net effect integrated over the full orbital period is a mass loss rate from the chromosphere that is higher, more irregular, and more directionally structured than what a single star would produce through its own winds and pulsations alone. The implication of that last point, higher and more irregular mass loss is the thing that connects this observation directly to the central problem of the destabilized timeline. Mass loss is the clock. It is the mechanism by which a massive star sheds the material that, if retained, would modify the pressure balance in its interior and alter the schedule of nuclear burning in its core. If Betelgeuse is losing mass faster than the standard models assumed, the remaining mass in its envelope is lower than the standard models calculated. If the remaining envelope mass is lower, the conditions in the core, the temperature, the density, the pressure, evolve on a different schedule. The lifetime estimate shifts, not to a specific new number, to an uncertainty range that is genuinely uncomfortable, and there is a layer to this that goes beyond just the mass loss rate. The act of periodic, orbital phase-locked perturbation of the chromosphere also means that the star is being driven, repeatedly and regularly, away from its natural equilibrium state. A single star in isolation has a characteristic way of responding to internal perturbations. Its pulsation, its convection, its magnetic activity all settle into a long-term balance that stellar models can describe fairly well. A star with an active companion inside its chromosphere is being constantly pushed away from that equilibrium. Every 5.78 years, the perturbation repeats. Every 5.78 years, the chromosphere is disturbed, outflows are enhanced, material is ejected, and the star has to readjust to the changed conditions in its envelope. This is not a one-time event. It is a periodic forcing function applied to a system that was already balanced on the edge of instability by virtue of being a massive evolved star in the late stages of its nuclear burning sequence. What the January 2026 Hubble result gave us, in the most precise terms, is the first empirical confirmation that Sawara is not just a proposed companion with an inferred orbit. It is an active physical agent that is doing measurable, repeatable, characterizable things to Betelgeuse's atmosphere every time it comes around. The evidence is no longer purely circumstantial. There is a signal in the data that requires this explanation. The companion is real, the interaction is real, and the consequences for the star's evolution, for how fast it is losing mass, for how its envelope is structured, for when its core will reach the conditions necessary for collapse, are also real. We just do not yet know how to quantify them precisely. The companion is not a passive observer, it is an active agent. And the most important single event in recent Betelgeuse research, the event that the public interpreted as a dusty hiccup, and the scientific community is still actively debating, may have been the first time we saw the agent's fingerprints on the visible face of the star. The great dimming was not the random occurrence it was initially sold as. It may have been a symptom, and the question of what exactly it was a symptom of is the question that reframes every assumption about the system's current state and future trajectory. Zessenderst, Part 4. The Great Dimming was misdiagnosed. Jostenderst. In the autumn of 2019, Betelgeuse began to get dark. Not suddenly. There was no single night where it dropped dramatically from its normal brightness. It faded gradually, the way a fire burns down rather than flares out. By December of 2019, observers were noticing that something was wrong. By January of 2020, the magnitude had dropped from its typical value of around 0.5 to approximately 1.6. For a star that has been one of the 10 brightest objects in the night sky for as long as humans have been recording star brightnesses, a drop of more than a full magnitude was not subtle. Betelgeuse, which normally blazes in the shoulder of Orion as one of the most easily recognizable stars in the Northern Hemisphere, had faded to a point where casual observers were remarking that Orion looked different, felt lopsided, was not quite right. The internet noticed, the scientific community mobilized. The initial explanations that circulated in the popular press were a mixture of reasonable inference and slightly breathless speculation. The most dramatic, and the one that made the most headlines, was that this could be the precursor to the supernova. The reasoning was simple and not entirely without logic. Betelgeuse was acting strange, and strange behavior in a massive evolved star is exactly what you might expect before a core collapse. The more measured scientific community pushed back on this quickly, noting that the dimming was gradual and the timescales did not match what we would predict for a pre-explosion event. But the conversation was happening, and it highlighted just how thin the line was between interesting variable behavior and potential precursor to the most dramatic event visible to the naked eye in 600 years. The first serious scientific explanation to gain traction was the dust hypothesis. Betelgeuse is known to be surrounded by extended shells of gas and dust, material it has ejected over thousands of years of stellar wind activity. Red supergiants are prodigious dust producers. The chemistry of their cool outer atmospheres allows silicate and aluminum oxide grains to form and be carried outward by radiation pressure. If a large episode of mass loss had recently produced a significant cloud of dust on the line of sight between us and the photosphere, that dust would absorb and scatter the star's light before it reached our telescopes. The result would be exactly what we were seeing, a dimming that was not related to any change in the star itself, but rather to something obscuring our view. This explanation is appealing in its simplicity, and there is real observational support for it. Dust clouds around Betelgeuse are not hypothetical, they have been directly imaged. The Very Large Telescope Array in Chile produced images showing asymmetric dimming of Betelgeuse's disk, with the southern portion appearing significantly darker than the northern portion, which is consistent with a dust cloud obscuring part of the star's visible face. But the dust-only explanation ran into a problem. A dust cloud blocks and scatters light, but it does not change the intrinsic temperature of the star's photosphere. If the dimming was purely due to dust, you would expect Betelgeuse's surface temperature to remain approximately constant. Only the apparent brightness as seen through the dust would change. And that is not what was observed. Multiple independent measurements of Betelgeuse's photospheric temperature during the dimming period showed a decrease of roughly 100 to 200 Kelvin. This is not a measurement artifact or an instrumental error. It was confirmed by multiple groups using multiple independent techniques. The star's surface actually cooled during the Great Dimming, and here is why that matters. A dust cloud cannot cool a star's photosphere. Those are two separate physical processes happening in two separate locations. The dust is outside the star, the photosphere is the star's surface. If the photosphere cooled, something happened inside the star, or at least at the level of the photosphere itself, that reduced the surface temperature. Dust alone cannot explain that. So the scientific community converged on what is now the consensus model, a hybrid explanation that is, in many ways, more interesting than either of its component parts alone. The sequence, as best as it can be reconstructed from the available data, goes something like this. A large-scale convective downflow event occurred in Betelgeuse's outer convective zone. Red supergiants are not like the Sun, with its relatively small convective cells that are spread uniformly across the surface. Betelgeuse has convective cells that can span a significant fraction of the stellar radius, structures so large that individual cells are actually visible as bright and dark regions on the stellar disk in high-resolution imaging. When a large convective downflow event occurs, a region where hot gas is being carried downward rather than upward, the surface above that region cools. The temperature drops, the star dims locally. The cooling of the surface has a secondary consequence that connects to the dust explanation. The outer atmosphere of Betelgeuse is full of heavy elements that have been dredged up from the nuclear burning zones deep inside. Silicon, aluminum, iron, and other elements that are not natural occupants of a stellar atmosphere, but end up there through the dredge-up processes that operate in evolved massive stars. These elements can form dust grains, but only if the temperature is low enough. Normally, the photospheric temperature is too high for most dust species to condense. But if the photospheric temperature drops by 100 to 200 Kelvin, enough to push the surface into the condensation temperature range for certain dust species, then grain formation can occur directly at or near the stellar surface. That newly formed dust then gets pushed outward by radiation pressure, positioning itself exactly on the line of sight, where it contributes additional dimming on top of the intrinsic dimming from the lower surface temperature. Dust was real. Cooling was real. But the cooling came first, and the cooling caused the dust. The dust was the symptom. The convective downflow event was the cause. And here is the point where the companion enters the picture in a way that should now feel structurally familiar from everything discussed so far. The timing of the Great Dimming, mapped against the orbital phase of Siwarha, is suggestive. Not conclusive. The orbital uncertainties are large enough that you cannot say definitively that Siwarha was in a specific part of its orbit during the dimming event. But the orbital phase during late 2019 and early 2020 corresponds to a window when the companion would have been in a portion of its orbit that, based on the UV observations from the Hubble study, corresponds to enhanced chromospheric perturbation. The outflows increase during this phase. The gas dynamics are more disturbed, and if the companion's passage through the chromosphere can drive perturbations that propagate downward into the convective zone, by modifying the pressure boundary conditions at the surface, by injecting momentum into the outer convective layers, by changing the thermal structure of the chromosphere above, then the Great Dimming may not have been a random internal event followed by a coincidental dust formation episode. It may have been a triggered event, caused or amplified by the companion's orbital transit. This is where the scientific community is genuinely divided. The causal chain from companion transit to convective disruption to photospheric cooling to dust formation is physically plausible. Each step in the chain has a reasonable mechanism, but plausible is not proven, and the uncertainties in the orbital phase, timing during the dimming event, leave enough room for skepticism. What is not in doubt is that the Great Dimming was more complex than the initial dust cloud story suggested. What is not in doubt is that the photosphere cooled. What is not in doubt is that the companion is real and is actively modifying the chromosphere. Whether those things are causally connected or merely coincident is still an open question. But the fact that the question can even be asked, that a companion inside the stellar envelope is now considered a viable co-trigger of the most dramatic variability event in Betelgeuse's recent history, is itself a sign of how thoroughly the model has changed. The dimming ended. By April of 2020, Betelgeuse was returning to its normal brightness, which produced another round of headlines declaring that the crisis was over and the star was fine. But was it? If the companion is real, then the perturbation that may have triggered the dimming has not gone away. It comes back every 5.78 years. The next orbital transit will bring Siwaha back through the same region of the chromosphere. The convective structure of the star is not the same as it was in 2019. Several years of continued evolution have changed the internal architecture. Will the next transit produce another large dimming event? A smaller one? A larger one? Something different entirely? We do not know. And that uncertainty, tied not to ignorance of the star's internal physics in isolation, but to ignorance of how an orbital interaction modifies that internal physics, is precisely what the destabilized timeline is made of. Voraussichten. Part 5. Convective collapse meets orbital trigger. Gises. The inside of Betelgeuse would be one of the most alien environments in the known universe. Not because the temperatures and pressures are extreme, though they are. The core is processing nuclear fuel at conditions that dwarf anything achievable in a laboratory. But because the convection, the churning of hot gas from deep inside toward the surface, operates on a scale that simply has no analogy in everyday experience. Our sun has convective cells. You can see their tops as the granulation pattern on the solar surface. Tiny, bright cells surrounded by darker edges, each one roughly the size of a large continent. The sun's convective zone is enormous by any human measure, but the individual cells are small relative to the star. Betelgeuse is different. The computer models of red supergiant convection, models that have become increasingly sophisticated over the last 2 decades as computational power has expanded, suggest that Betelgeuse's convective cells can span anywhere from 20 to 40% of the stellar radius. That means a single convective cell in Betelgeuse could be hundreds of times the radius of the entire Sun. These are not small-scale mixing structures homogenizing the stellar interior. These are planetary-scale upheavals of superheated plasma, rising slowly over months or years, expanding as they approach the surface, radiating their energy, and then sinking back down on timescales comparable to the star's pulsation cycle. When you look at high-resolution images of Betelgeuse's disk, the irregular brightness patterns you see, some regions brighter, some darker, are the tops of these convective cells. This is the physical environment into which Siwaha is plunging on every orbital pass. It is not a smooth, uniform medium. It is a boiling fluid operating at scales comparable to the companion's orbital radius. And the question of how a companion's gravitational and aerodynamic influence couples to convective flows of this size is, to put it charitably, not a solved problem. The analytical tools that work well for small perturbations in well-behaved systems become unreliable when the perturber is the same size as the structures being perturbed and when the medium is itself highly dynamic and poorly constrained. This is frontier physics, and the frontier is wide. What can be said with reasonable confidence is that the companion's passage through the chromosphere modifies the pressure and thermal boundary conditions at the top of the convective zone. Convection in a stellar envelope is driven by the temperature gradient, the difference in temperature between the hot deep interior and the cooler outer surface. If the surface conditions are modified, if a companion transit deposits momentum and energy into the chromosphere, changing the effective temperature at the top of the convective zone, then the driving force for convection changes. This is a feedback mechanism. You're not just watching convection happen, and then separately watching the companion interact with the atmosphere. You're watching a coupled system where the companion's orbit modifies the convection, and the convection modifies the atmosphere through which the companion is moving, and the companion's interaction with that modified atmosphere produces further changes in the convection. The analogy that comes to mind is stirring a pot of boiling liquid. Before you stir, the convection is organized. Large, stable, convective rolls carry heat from the bottom to the top in an efficient, structured way. The moment you introduce an external perturbation, the spoon moving through the liquid, the organized pattern breaks up. New eddies form. The heat transport becomes irregular. Different regions of the pot develop different temperature profiles. If you stir repeatedly on a regular cycle, the pattern of convection never fully settles back into its pre-stirring organization before the next perturbation arrives. The pot develops a persistent memory of the perturbations, and its behavior becomes a superposition of its natural convective instincts and the externally imposed rhythm of the spoon. This is what the orbital interaction with Siwaha may be doing to Betelgeuse's convection on a timescale of millions of years. The companion has been there, if it formed with the system, since the beginning. Every 5.78 years it stirs the pot. The convection in Betelgeuse has been evolving in the presence of this periodic forcing for as long as the system has existed. What we observe today is not Betelgeuse's natural convective state. It is Betelgeuse's convective state as shaped by millions of years of interaction with a companion that our models did not account for. Now, to connect this back to the central problem, the destabilized timeline, consider what convection does in the late stages of a massive star's evolution. The convective envelope is not just a heat transport mechanism. It is also a mixing machine, dredging material from the nuclear burning zones deep inside the star up to the surface and carrying surface material back down. This dredge-up process controls the chemical composition of the envelope, which in turn controls the opacity of the envelope, which in turn controls how the star loses mass through its stellar wind. Mass loss from a red supergiant is not just about how hot the surface is or how strong the radiation pressure is. It is also about the chemistry of the atmosphere. How much dust-forming material has been dredged up from the interior, how much of it condenses into grains near the surface, and how efficiently radiation pressure can drive those grains outward and carry gas along with them. If the companion's orbital interaction has been modifying the convective pattern for millions of years, amplifying some mixing episodes, disrupting others, creating intervals of enhanced dredge-up followed by suppression, then the chemical composition of Betelgeuse's envelope is not what it would have been without the companion. The opacity is different. The mass loss rate is different. The star that exists today is not the star that the single-star evolution tracks describe, and the star that will exist in 1,000 years, or 10,000 years, or 100,000 years, if it lives that long, will continue to evolve under the influence of these periodic perturbations in ways that are simply not captured by any existing model. This is not a comfortable place to be scientifically, but it is an honest one. And the honesty has consequences not just for Betelgeuse but for the broader field of stellar evolution, because if one of the most intensively studied red supergiants in the sky turns out to have a hidden companion driving its evolution in ways we missed for decades, it raises an obvious and deeply uncomfortable question about all the others. Part 6. Episodic mass loss, the missing piece. For most of the history of stellar astrophysics, mass loss from red supergiants was modelled as a steady wind. Not a hurricane, more like a persistent breeze, continuous and smooth, the rate varying slowly as the star evolved but always characterised by a single number that could be plugged into the evolutionary tracks. This single number, the mass loss rate, typically expressed in units of solar masses per year, determined almost everything else about the star's future. Feed in the mass loss rate, and the model will tell you how long the star lives, how much mass it retains when it dies, whether the explosion will be particularly energetic or relatively quiet, and what kind of remnant will be left behind. The mass loss rate was treated as a fundamental parameter, uncertain in its precise value, but conceptually simple in its structure. We now know that this picture is incomplete. Not slightly incomplete, wrong in structure. Mass loss from red supergiants is not a smooth, steady wind. It is episodic. It comes in bursts. The star can eject significant quantities of material in a relatively short time, then quiet down, then erupt again. The timescale and trigger mechanism for these episodes vary from star to star and, as the Betelgeuse case is now suggesting, may depend critically on whether the star has a close companion. The evidence for episodic mass loss in Betelgeuse specifically comes from multiple sources. The multiple circumstellar shells observed around Betelgeuse, the concentric rings of ejected material that surround the star at distances ranging from a few stellar radii to several light-years, are themselves evidence of episodic ejection. A steady wind does not produce discrete shells. It produces a continuous density profile that decreases smoothly with distance. Shells require events, specific episodes of enhanced mass loss that ejected material in bursts, which then expanded outward and are now observed as distinct rings. Betelgeuse has several of these shells, with different densities and sizes, implying multiple past ejection episodes of different intensities. The timescales between ejection episodes, estimated from the distances and expansion velocities of the shells, range from hundreds to thousands of years. The UV observations from Hubble add another dimension to this picture. The phase-locked outflow signatures that were described earlier, the enhanced velocities and increased absorption features that appear in the orbital phase windows corresponding to Siwara's transit through the chromosphere, are not steady. They appear, strengthen, and then gradually diminish over the weeks and months following the transit, as the perturbed gas either falls back or escapes to larger distances. This is the structure of an episodic ejection event, not a steady wind. The companion's passage creates a window of enhanced mass loss, and then that window closes until the next orbital pass. This pattern, if it is real, and if it applies to the full mass loss budget and not just the UV visible component, means that Betelgeuse loses mass impulses synchronized to the 5.78-year orbit. Every 5.78 years, there is an episode of elevated mass loss. Between episodes, the mass loss rate returns to its lower quiescent value. The time average mass loss rate might not be dramatically different from the single star estimates, or it might be significantly higher. We do not have the long baseline data to average over enough orbital cycles to be sure. But the structure of the mass loss is definitely not what the steady wind models assume, and the structure matters because episodic mass loss changes the chemical and physical properties of the circumstellar environment in ways that feed back into the star's own evolution. The Betelgeuse story is not unique in this regard. Antares, the other red supergiant bright enough to observe in similar detail from Earth, also shows evidence of a symmetric, structured mass loss that does not fit cleanly into steady wind models. Vius Canis Majoris, one of the most extreme red supergiants known, has an extended circumstellar environment of extraordinary complexity. Multiple arcs, knots, and filaments of ejected material in different directions and at different distances, implying a history of highly variable, directionally anisotropic mass loss events. Whether VY Canis Majoris has a close companion driving some of this complexity is not established, but the question is now being asked more seriously than it was before the Betelgeuse results. And this is where the implications of the Betelgeuse case start to expand outward from one system to a broader scientific challenge. If hidden close companions are contributing to episodic mass loss in some or many red supergiants, and if those companions have been systematically missed because we modelled these stars as isolated objects, then the mass loss rates in our stellar evolution databases are not just wrong for Betelgeuse. They may be systematically biased for a significant fraction of massive evolved stars. The stellar evolution tracks that underpin our understanding of how massive stars die, the tracks that tell us how many neutron stars and black holes form per unit time in a galaxy, how the chemical enrichment of the interstellar medium proceeds, how the demographics of supernovae are expected to look. All of those tracks are built on mass loss rates derived from observations of stars that may not be as isolated as we thought. This is not a catastrophic failure of stellar physics. The basic physics is sound. The nuclear burning sequences are well understood. the gravity and pressure equations are not in question. But the boundary conditions, the mass loss rates that set the pace of evolution in the outer layers, may have been systematically underestimated for stars in interacting binary or near-binary configurations, which, as we are now learning, may be more common than we assumed. The consequence is that the universe has been making neutron stars and black holes on a schedule that our models have been slightly misrepresenting. How slightly? That is the question that the next generation of surveys, combining long baseline radial velocity monitoring, precision astrometry, and ultraviolet spectroscopy, will hopefully begin to answer. In the meantime, what the Betelgeuse case has given us is a proof of concept. It has demonstrated that a star we thought we understood completely, one of the most observed objects in the night sky, subject to over a century of continuous photometric monitoring and decades of high-resolution spectroscopy, was harbouring a companion that was actively modifying its evolution in ways we completely missed. If it can happen for Betelgeuse, the canonical nearby red supergiant, it can happen for any of them. The reassuring story of stable, well-characterized stellar evolution may be in significant part a story we told ourselves because we were only seeing half the picture. 1 Nan, Part 7, 1386. The sky we see is historical. Here is a thought experiment. Imagine you receive a letter from a friend. You read it, and the letter describes their life in vivid, specific detail. Their health, their relationships, their plans for the future, their worries. The letter tells you everything you could want to know about how they were doing when they wrote it. Now imagine that the postal system used to deliver the letter took 620 years. The friend who wrote it is dead. Not only are they dead, everyone who knew them is dead. Everything they described in the letter happened in a world that no longer exists. The plans they mentioned have either succeeded or failed or been forgotten. The worries have either materialized or passed. You're reading a document of historical record, not a message from a living correspondent. But the letter arrived today, so it feels present. It feels current. It feels like information about now. This is what it means to observe Betelgeuse. The light that reaches your telescope tonight, the photons that your eye or your detector registers as a signal from that reddish point in Orion's shoulder, left Betelgeuse at a distance that most measurements place between 548 and 640 light-years. The most commonly cited estimate in recent literature is in the range of 550 to 620 light-years. Let us use 600 light-years as a round number for the purpose of grounding this in a timeline that is humanly meaningful. 600 light-years means that the light we are seeing tonight left Betelgeuse approximately 600 years ago. 600 years ago in our calendar puts us at around the year 1426. That is 2 decades before Johannes Gutenberg developed movable type printing in Europe. It is before Columbus crossed the Atlantic. It is before Leonardo da Vinci was born. It is before the Ottoman conquest of Constantinople. The light that is currently entering our telescopes was already travelling through space when the 100 Years' War was still being fought, when the Ming dynasty was consolidating its control over China, when the Aztec Empire was in its early stages of expansion, when the Kingdom of Mali was at or near its height under Musa III. That is the age of the light we're receiving. That is how old our most current observations of Betelgeuse actually are. But wait. The estimate of 600 light-years has its own uncertainty. Some measurements place Betelgeuse closer, around 548 light-years, while others push it further, to 640 or even more. The distance uncertainty in Betelgeuse is embarrassingly large for a star that has been studied this intensively, and it exists because measuring stellar parallax, the tiny shift in apparent position that a star shows as Earth orbits the Sun, is exceptionally difficult for large diffuse stars like red supergiants. The surface of Betelgeuse is not a point. It is a disk with a finite angular size, and the centre of that disk wobbles as convective cells rise and fall. When you try to measure the parallax of something that is wobbling due to internal convective motions, your parallax measurement is contaminated by those motions, and the derived distance carries a correspondingly large uncertainty. What this distance uncertainty means in practice is that when we talk about the light arriving from Betelgeuse, we cannot be more precise than sometime in the 14th century. If the distance is 548 light-years, Then the light we see tonight left the star in the year 1478. If the distance is 640 light-years, the light left in 1386. The range of possible emission dates for tonight's photons spans nearly a century of Earth history. The great dimming that we observed in 2019 and 2020, that dramatic, puzzling drop in brightness that triggered global excitement and genuine scientific debate, corresponds to something that actually happened to Betelgeuse somewhere between 1380 and 1470, depending on which distance estimate you use. Let that sink in for a moment. The event we have spent the last 6 years analysing, building models for, arguing about in the literature, and now connecting to an orbital companion and its chromospheric wake. That event is a piece of 14th century history. We are not studying what Betelgeuse did recently. We are studying what it did during the late medieval period, and the light from those events is only now reaching us. The scientific papers we are citing are historical documents, not current reports. The star we are describing in present tense, Betelgeuse, is losing mass, the companion is perturbing the chromosphere, the outflows are increasing. All of those present tense statements are, in the most literal physical sense, past tense statements. They describe how the system was behaving when the light was emitted. They tell us nothing about the state of the system right now. This is not a minor semantic quibble. It has a real and significant consequence for everything we are discussing. The companion Siwaha, its orbital parameters, its phase-locked interaction with the chromosphere, its role in driving enhanced mass loss. All of that is inferred from observations of a system in its state 600 years ago. The inference is valid for that past state. But the star has continued to evolve since that light was emitted. 600 years is not a long time on stellar timescales. Betelgeuse's remaining lifetime, even in the most pessimistic new estimates, is measured in thousands of years at minimum. So the broad strokes of the system's structure probably have not changed dramatically. But the details, the specific orbital phase, the current state of the chromosphere, whether another large convective event has occurred, whether the mass loss rate has changed, are unknowable. We have no data on those questions. We cannot have data on those questions. The data does not exist yet. It is still in transit. And then there is the most dramatic version of this thought experiment, the one that tends to make people go quiet for a moment when you state it directly. What if the supernova has already happened? Not in the sense of an imminent event we are waiting for, but in the sense that the explosion might have already occurred in Betelgeuse's time, and the light from that explosion has not yet reached us. If Betelgeuse went supernova 300 years ago, in Betelgeuse's time, sometime around what would be the 17th century by our calendar, then the light from that explosion is currently travelling toward us, already on its way, and it will arrive at some point in the next 200 to 300 years. We would see it, suddenly and dramatically, on a night that currently does not look special in any way. The star that appears tonight in the shoulder of Orion is, in that scenario, already gone. We are seeing a ghost. We are watching a light that was emitted by something that no longer exists. This is not a certainty. There is no evidence for an explosion having occurred. The light from a supernova would propagate outward in all directions and might interact with surrounding structures in ways that would produce secondary signals before the direct light reached us. But those secondary signals would also require centuries to arrive, so even that would not help. There is, however, one kind of signal that travels through space in a way that could give us advance warning, and it is not electromagnetic radiation at all. Business Test. Part 8. The present tense is a fiction. The phrase, Betelgeuse is a red supergiant, is technically a lie. Not intentionally, not maliciously, but literally in the strictest physical sense. It is a statement about the past dressed up in present tense clothing. Every statement we make about Betelgeuse's current state, its luminosity, its temperature, its mass loss rate, the orbital phase of its companion, the structure of its chromosphere, is a statement about how the system was configured when the relevant light was emitted, which is to say between 5 and 7 centuries ago. The word is does not apply to any object separated from us by light travel time. It cannot. There is no mechanism for information to travel faster than light. The present state of Betelgeuse is, in an absolute and non-negotiable physical sense, inaccessible to us. This might seem like philosophical hair-splitting. In everyday life, we treat distant objects as existing in the present. The moon is 240,000 miles away, so the light from it is only about 1.3 seconds old. The present of the Moon is close enough to our present that the distinction is irrelevant. Even the Sun is only 8 light minutes away. But Betelgeuse is 600 light years away, and 600 years is long enough for significant things to happen. It is long enough for an entire stellar evolutionary phase to advance perceptibly. It is long enough for a companion to complete over 100 orbital cycles. It is long enough for the convective structure of the envelope to reorganize multiple times. We are not seeing a live broadcast, we are watching a recording, and the recording ended 600 years ago. So what is Betelgeuse doing right now, in the present of our moment, the year 2026 on Earth? The honest answer is, we do not know. Several possibilities exist, and they are not all equally likely, but none can be ruled out on the basis of currently available evidence. The system could be in a stable phase of its normal evolution, plodding along toward a supernova that is still many thousands of years in the future. The orbital interaction with Siwara could be proceeding normally, the companion somewhere in its 5.78-year orbit, the chromosphere being perturbed in its regular cyclical way. The star could be in a quiet phase between large convective events, or it could be in the middle of another dimming event comparable to 2019 and 2020. All of these scenarios are consistent with what we observe, because what we observe is 600 years old, and all of these scenarios are consistent with the state of the system 600 years ago. There are also more dramatic possibilities that cannot be ruled out, though the probability of the most extreme scenario occurring in exactly this historical window is low. The system could be in the middle of a particularly intense mass loss episode driven by a strong orbital interaction. The mass loss could have crossed the threshold that some models associate with rapid envelope stripping. The companion and the primary could be in a phase of enhanced tidal interaction that is driving structural changes in the core indirectly through envelope evolution. Or, and this is the scenario that tends to grab attention, the star could already have collapsed. The core, having finally exhausted its nuclear fuel through a sequence of burning stages that ended in iron, the one element whose fusion does not release energy, could have collapsed in a fraction of a second, sending a shockwave outward through the star and producing a supernova. The light from that explosion, travelling at the speed of a light, would be on its way here. We would not know until it arrived. This is not a scenario that any current model considers likely in the very near term. The observable evidence from 600 years ago suggests a system that was not in the final stages of collapse. But not likely in the near term is not the same as impossible. The uncertainty in the remaining lifetime, driven by the unknown impact of the companion on mass loss and core evolution, is large enough that scenarios with very short remaining lifetimes cannot be excluded on physical grounds. The flaw has been removed from the probability distribution. The minimum possible remaining lifetime is not well constrained. It was, it no longer is. And so, the fiction we tell ourselves, when we say, Betelgeuse is a red supergiant, or Betelgeuse will explode eventually, or Betelgeuse is losing mass right now, is a necessary and practical fiction. We have to speak in present tense about it. We cannot insert a 600-year time delay qualifier into every sentence. But when we do, we should hold somewhere in the back of our minds the knowledge that all of those statements are historical. We are describing a past state. The present state is unknown. And the event horizon between our knowledge and our ignorance is drawn by the speed of light, which nothing, no telescope, no calculation, no theoretical model can exceed. There is, however, one exception. One physical process that might breach that information barrier, not by travelling faster than light, but by starting its journey to us before the light from the explosion has even left the star. And that process is so strange, so counterintuitive, and so fundamental to the physics of core collapse that it deserves its own careful consideration. 1 Kern, Part 9. The only signal that beats light. 1 Kern. Core collapse is not instantaneous, not in the way a light switch flips. The process unfolds over a sequence of stages that have distinct timescales, and during the early stages of that sequence, the star's outer layers have not yet received any information that anything has changed deep inside. The core collapses, it bounces, it produces a shockwave. The shockwave begins propagating outward through the star at a significant fraction of the speed of sound in the stellar material, not the speed of light, not anything close to it. It will take the shock wave somewhere between a few minutes and a few hours to reach the outer layers of the star and begin the process of driving the explosion visible from outside. During that window, the star still looks normal. The photosphere is still radiating quietly. The companion is still on its orbit. The chromosphere is still being perturbed. Nothing visible has changed. But something invisible has changed completely. The core, in the moment of collapse, undergoes a catastrophic reorganization. Matter is compressed beyond the density of nuclear material. Protons and electrons are forced together to form neutrons. The energy released in this process is staggering, roughly 3 times 10 to the 46th joules, which is more energy than the Sun will radiate over its entire 10 billion year lifetime. About 99% of this energy is radiated not as light, not as sound, not as heat, but as neutrinos. Neutrinos are subatomic particles with almost no mass and no electric charge. They interact with matter only through the weak nuclear force, which makes them the most penetrating particles in existence. A neutrino can pass through a light year of solid lead without interacting with a single atom. They pass through planets, through stars, through the earth beneath your feet, as if the matter were not there. This extraordinary penetrating power means that when the core of Betelgeuse collapses and produces its flood of neutrinos, those neutrinos do not wait for the shockwave to reach the photosphere. They do not wait for the star's outer layers to be informed that the core has failed. They stream outward through the collapsing core, through the overlying mantle, through the entire volume of the star and exit into space, headed in all directions, including toward Earth, within seconds of the core bounce. Meanwhile, the shockwave is still working its way outward through the stellar interior. The light that will eventually make Betelgeuse visible as a supernova is still hours away from escaping the star. But the neutrinos are already in space, travelling at very nearly the speed of light, carrying the news of the collapse outward in all directions. This is the neutrino early warning. The neutrinos from a Betelgeuse supernova, approximately 10 to the 58 of them, a number so large it requires you to stop and contemplate it for a moment, will arrive at Earth somewhere between 2 and 48 hours before the first light from the explosion is visible. The exact timing depends on the star's distance, which is uncertain, and on the specific dynamics of the explosion, which we cannot observe in advance. But the window is real. The neutrinos will come first, and we will know they are there, not because you can see or feel or detect them with any ordinary instrument, but because of a network of extraordinary detectors that have been built precisely for this purpose, buried under mountains and under the ocean floor and under Antarctic ice, waiting. The Supernova Early Warning System, SNEWS, is a coordination framework that connects multiple large-scale neutrino detectors around the world. The detectors include Super Kamiokande, a 50,000-ton tank of ultra-pure water buried under a mountain in Japan, whose inner surface is covered with thousands of photomultiplier tubes watching for the rare flash of Cherenkov radiation that occurs when a neutrino interacts with a water molecule. They include the Ice Cube Neutrino Observatory at the South Pole, where a cubic kilometre of Antarctic ice has been instrumented with thousands of sensors sensitive to the same kind of interaction. They include detectors in Europe, in North America, and elsewhere. Each of these detectors is sensitive enough to detect the neutrino burst from a supernova within our galaxy, with extremely high confidence. The SNEW system works on coincidence. A single detector seeing an anomalous burst of events could be a statistical fluke, a cosmic ray event, an instrumental artifact. But 2 or more geographically separated detectors seeing the same kind of burst within a coincidence window of 10 seconds is, in the context of this kind of experiment, essentially impossible to explain as a coincidence. The probability of a false alarm from random backgrounds is so low that when the coincidence trigger fires, the only serious explanation is a real astrophysical event. When that happens, the SNEW system automatically generates and distributes an alert to the global astronomical community, observatories, space-based telescopes, individual astronomers around the world, within minutes, not hours, minutes. The alert will contain information about the estimated direction of the source, determined by small timing differences between the arrival of the neutrino burst at detectors at different locations on Earth, the total number of detected neutrinos, which constrains the energy of the collapse, and the uncertainty on all of these quantities. The mathematical details of how many neutrinos Super Kamiokande alone would detect from a Betelgeuse supernova are remarkable. Based on the expected distance and the standard core collapse neutrino flux, Super Kamiokande would register somewhere in the range of 5,000 to 10,000 individual neutrino interactions in the span of about 10 seconds. For comparison, the detectors on Earth detected 25 neutrinos from supernova 1987A, which exploded in the Large Magellanic Cloud at a distance of roughly 160,000 light-years. Betelgeuse is somewhere between 250 and 300 times closer than that, and because neutrino flux scales with the inverse square of distance, the neutrino yield from a Betelgeuse supernova would be roughly 60,000 to 100,000 times greater per detector. The detectors would be saturated with events for several seconds. The signal would be unmistakable. This is the one way in which the 600-year light travel delay is partially circumvented. The supernova itself cannot be observed until the light reaches us, but the internal collapse, the moment the core goes, the moment the neutron star forms, the moment the explosion begins, will be announced by a neutrino burst that reaches Earth hours before the photons from the blast. That window, 2 to 48 hours of advance knowledge, is, in the context of preparing astronomical facilities and alerting the public, enormously valuable. Every telescope on Earth and in space can be pointed at Betelgeuse before the light arrives. Every detector system can be put into its higher sensitivity mode. Every photometric and spectroscopic facility can be ready to capture the early light curve, the shock breakout flash, the first hours of the explosion, events that have never been observed in real time for a supernova this close, and that contain information about the explosion mechanism that cannot be recovered after the fact. And then the light arrives. Whatsies. Part 10. The moment the alert fires. Wow. You're asleep when it happens, or you're working, or sitting in a restaurant, or scrolling through your phone in that half-conscious way you do when the evening has run out of things to offer. Nothing about the moment announces itself. The sky outside looks exactly the way it always does. Orion is where Orion always is. The left shoulder burns its familiar orange-red. Everything feels normal. And then, somewhere under a mountain in Japan, inside a tank of ultra-pure water, the size of a large building that has been sitting in the dark for decades, something changes. A burst of neutrinos arrives from the direction of Orion. Not one or two, not the kind of sporadic background signal the detector registers on any ordinary night from cosmic rays and atmospheric interactions. Thousands of them. In the span of 10 seconds, several thousand individual neutrino interactions register in the detector, each one producing a tiny flash of blue Cherenkov light as the neutrino transfers its energy to an electron in the water, and each flash caught by one of the thousands of photomultiplier tubes lining the inner surface of the tank. The data cascades through the acquisition system faster than any human operator could possibly pass it in real time, but the automated analysis code does not need a human. It runs in milliseconds, it counts the events, it compares the rate to the background model, the number crosses the threshold that the system was designed to recognize, and the first flag is raised. The coincidence check fires almost simultaneously. Halfway around the world, buried under a cubic kilometre of Antarctic ice at the South Pole, IceCube has registered its own burst. The timing offset between the two detections, a matter of milliseconds, matches exactly what the geometry of the detector positions and the arrival direction of the signal would predict if the source were in the direction of Orion. This is not a coincidence. Coincidences do not respect geometry to millisecond precision. 2 more detectors report matching signals within seconds, one in Europe, one in North America, each offset from the others by exactly the light travel time between their physical locations. The snooze coincidence trigger activates. The supernova early warning system, which was built for exactly this moment, and which its designers hoped would never be needed in their lifetimes, while also desperately hoping it would be, has fired for the first time in its operational history with a genuine astrophysical event. Within minutes, automated alerts propagate outward through the subscriber lists that connect virtually every major observatory on Earth and in space to the snooze network. It is the middle of the night in some time zones and the middle of the working day in others, and it does not matter. Phones buzz in astronomers' pockets during dinner and during departmental meetings and in the middle of observing runs on completely different targets. Email servers route urgent flags to telescope operators, mission control centers, university departments, space agency operations rooms. The language in the alerts is careful, precise, and deliberately restrained. estimated source direction consistent with Betelgeuse, statistical significance exceeding 5 sigma, all major detectors in coincidence, supernova event strongly indicated. But the meaning is not ambiguous to anyone who reads it. There is no secondary interpretation. There is no, could be an instrumental artifact, please investigate. This is the one. Every person in professional astronomy who receives that alert understands immediately in the first second of reading it that this is the event their entire field has been building toward for decades. The infrastructure, the detectors, the coordination protocols, the rehearsals, all of it was constructed in preparation for this specific moment. The response that follows is unlike any coordinated effort the astronomical community has ever attempted. Space telescopes receive commands to slew to Betelgeuse's coordinates, interrupting whatever they were doing, abandoning whatever observation had been scheduled, because nothing else in the observable universe is as scientifically valuable right now as what is about to happen in the left shoulder of Orion. Ground-based observatories across every time zone and the global distribution of astronomy facilities was designed, in part, precisely so that no event in the sky would be invisible to all of them simultaneously, begin queuing specialized observation programs, radio telescopes which can track the expanding shockwave and the eventual pulsar if one forms, X-ray telescopes which will record the shock breakout, the brief, brilliant flash of high-energy radiation that occurs when the shockwave from the collapsing core finally punches through the stellar surface, optical telescopes in every aperture class, from the largest ground-based mirrors in Chile and Hawaii to the amateur instruments in suburban backyards, infrared observatories tracking the thermal evolution of the expanding ejecta. Every instrument on Earth and in orbit that can be pointed at a single coordinate is now pointed at that coordinate, and the coordinate is one that astronomers have been pointing instruments at for over a century. The light has not arrived yet. It is still hours away. The neutrinos, nearly massless and completely indifferent to the matter they pass through, made the journey from Betelgeuse to Earth at almost exactly the speed of light. The photons from the explosion are also travelling at the speed of light, but they started their journey later. They had to wait for the shockwave to work its way outward through the entire volume of the collapsing star before they could escape. That journey through the stellar interior, even at a significant fraction of the speed of sound in the dense material, took hours. So the neutrinos arrived first, as they were always going to, and the light is following behind, and right now the window between the neutrino detection and the first photons is the most scientifically valuable gap of time in the history of observational astronomy. The public learns about it not through a formal announcement from any government or agency. There is no press release, there is no scheduled briefing. What happens instead is exactly what happens with every piece of genuinely significant breaking news in the current era. It propagates through social media, unevenly and then suddenly everywhere, carried by astronomers and observatory staff and the science communicators who have spent years building audiences precisely for moments like this. Within an hour of the neutrino detection, the shape of what is happening is circulating widely. Betelgeuse, neutrino burst, supernova, confirmed. The accounts that have spent years patiently explaining stellar physics and the destabilization evidence and the companion Siwaha and the light delay problem to audiences of curious non-specialists suddenly have something unprecedented to communicate. Not a theoretical prediction, not a model output, not an eventually in some uncertain future, an imminent event, hours away, visible to the naked eye, the closest supernova observable with modern technology in the entire history of astronomy. This is also, and I want to say this clearly because it will need to be said clearly many times in the hours that follow, completely safe. The distance to Betelgeuse, somewhere between 550 and 640 light-years depending on which measurement you trust, is more than 2 orders of magnitude beyond the range at which a supernova could plausibly affect Earth's biosphere. The harmful radiation, X-rays, gamma rays, high-energy particles, falls off with the inverse square of distance, and at 600 light-years, the flux from even an unusually energetic explosion is orders of magnitude below any biological threshold. The neutrinos that just triggered every detector in the snooze network are, at this moment, passing through every human body on Earth, through the oceans, through the mantle, out the other side, and continuing outward into space. Not one of them interacted with you. You did not feel them. You will never feel them. The light will be extraordinary. The experience will be transformative in ways that are difficult to predict, because nothing like it has happened in the lifetime of anyone alive, but it will not hurt anyone. The danger from a Betelgeuse supernova is approximately equivalent to the danger from a very bright sunrise, which is to say, none. What the hours between the neutrino alert and the first visible light will feel like is something that genuinely has no precedent in human experience. It is not like waiting for an eclipse, which is predictable to the second, and whose mechanism is completely understood, and whose visual effect is known in advance. It is not like waiting for a storm where the uncertainty is about severity rather than the nature of the event. It is collective anticipation of a cosmic transformation, the death of a star that has been in the human sky since before writing existed, announced by the most exotic particles in nature, hours before anyone can see it. People in cities will look up at Orion and locate the left shoulder and watch it, knowing that what they are seeing is 600-year-old light, knowing that what is coming is something different. Amateur astronomers will carry their telescopes to dark spots. Schools and planetariums will open their doors in the middle of the night. Astronomers will give interviews from observatory domes while simultaneously monitoring their instrument feeds. The internet will be the most focused and most chaotic it has ever been, simultaneously routing real scientific information and an enormous volume of everything else. And then, quietly at first, so quietly that the first reports will wonder if it is an artifact of expectation, a trick of dark adapted eyes looking too hard at a single point. From a position in the left shoulder of Orion, from a point that has held its place in the human sky for as long as there have been human eyes to observe it, a new light will begin to grow. Landsat, Part 11. The first 24 hours. Landkand. The first thing to understand about a supernova is that it does not begin with light. By the time the first photon from the explosion reaches your eye, the event that caused it has already been underway for hours. The core collapsed, the neutron star formed. The shockwave began its journey outward through 17 solar masses of stellar material. All of that happened before a single visible photon escaped the star. What you see, when you finally see it, is not the beginning. It is the moment the explosion finally punched its way out. That moment is called the shock breakout, and it is brief in the way that the most intense things tend to be brief. As the shock wave that originated in the collapsing core finally reaches the stellar surface, after travelling through the entire volume of a star 700 times the radius of the Sun, it deposits an enormous quantity of energy into a thin layer at the photosphere. Not gradually, suddenly. The energy has nowhere else to go, and it radiates away in a burst of X-rays and extreme ultraviolet radiation. Not the orange-red glow you associate with Betelgeuse, but hard, high-energy light that carries the imprint of temperatures far exceeding anything the star's surface produced during its entire 10-million-year lifetime. This flash lasts for minutes to hours depending on the size of the progenitor, and because Betelgeuse is one of the largest stars we know of, the breakout will be on the longer end of that scale. The shockwave had a longer journey, more material to push through, more time between ignition and emergence. Space telescopes in ultraviolet and X-ray bands will record this in a level of detail that was simply not available for any previous supernova of scientific interest. Supernova 1987A, the last nearby supernova we observed with modern instruments, exploded in the Large Magellanic Cloud at a distance of 160,000 light-years. The shock breakout from that explosion was detected only in hindsight, from archival data, not in real time. Betelgeuse is roughly 300 times closer. The shock breakout signal, adjusted for distance, will be orders of magnitude brighter in our detectors. We will watch it happen in real time, with instruments specifically prepared and waiting because the neutrino alert gave us hours of advance notice. This is an unrepeatable scientific opportunity, and the people who built those instruments and spent careers preparing for this moment will be the ones sitting at their screens watching the data arrive. For anyone watching from the ground with their eyes, the first signal will be subtler. In the minutes following shock breakout, Betelgeuse will begin to brighten, not dramatically, not all at once, but measurably, detectably, in a way that will be immediately apparent to anyone with even a modest telescope who happens to be pointed at the right part of Orion. Slowly at first, then faster. The physics driving this early brightening is the expanding fireball of ejecta, material that was the star's outer layers, now moving outward at thousands of kilometers per second, releasing the energy of the explosion as it expands and its surface area grows. More surface area means more total emission. The luminosity climbs as the fireball grows. By the end of the first full day, the transformation will be complete enough that no one who steps outside will miss it. Exactly how bright Betelgeuse will be at peak is genuinely uncertain, because the peak brightness depends on parameters we do not know in advance. The total kinetic energy of the explosion, the mass of the ejector, the structure of the outer envelope, and critically, whether that envelope has been significantly modified by Suwarrow's long history of orbital interaction. A companion that has been plunging through the chromosphere on a 5.78-year cycle for potentially millions of years may have carved preferential channels into the envelope, created asymmetric density structures, altered the opacity in specific directions. All of those modifications affect how the explosion propagates outward and how efficiently the energy is converted into visible light. The standard models give us a range. Early estimates suggest peak brightness somewhere between magnitude -6 and magnitude -9. Let me translate those numbers into something that makes visceral sense. Venus, at its absolute brightest, reaches about magnitude -4.6, bright enough to cast a faint shadow on a very dark night, bright enough to be visible in daylight if you know exactly where to look. The full moon sits around magnitude -12.7. A Betelgeuse supernova at the brighter end of the predicted range would be significantly more luminous than Venus but still short of the full moon, somewhere in the territory of easily visible in broad daylight, bright enough that people who have never once in their lives noticed Venus in the daytime sky will see this without being told where to look. At the fainter end of the prediction range, it will still be the most spectacular stellar object that anyone alive has ever seen. There is no version of this event that is underwhelming. During the first night following the explosion, assuming the timing places the light arrival during daylight hours in some parts of the world, the first night could be a matter of hours after detection. Betelgeuse will be the brightest point of light in the sky by a margin that will make the comparison almost embarrassing. Every other star will look like background noise, and the colour will not be static. The expanding fireball in its early hours will be radiating from material that has been shock-heated to extreme temperatures, blue-white, hard, the colour of something very young and very violent. As the ejector expands and cools over the following hours, the colour will shift. Blue-white to yellow-white to the warmer tones of a cooling plasma, passing through hues over the course of a single night that would take a normal star millions of years to traverse on the main sequence. Any attentive observer watching through even modest binoculars will be able to see this evolution. Time-lapse sequences shot on ordinary camera equipment will show the brightening progressing in real time. Long exposure photographs will begin to reveal structure in the expanding envelope, asymmetries, extensions, the first hints of a shape that the naked eye cannot resolve but that the cameras will catch. And the science happening in parallel with all of this spectacle will be extraordinary in ways that are difficult to fully convey. Shock breakout carries encoded within it the density structure of the star's outer layers at the moment of explosion, the mass loss history, the envelope composition, the imprint of every outflow event that happened in the last several thousand years. Every orbital pass of Suwarrow that enhanced the mass loss, every convective event that drove dust formation, every episodic ejection that created the concentric shells we can image in the circumstellar environment. All of that history is written into the structure of the photosphere and chromosphere that the shockwave just destroyed, and the early light from the explosion is carrying that information outward at the speed of light, directly into our waiting spectrographs. The early spectroscopic observations, taken in the first hours after the light arrives, will show the composition and velocity structure of the outermost ejector. If Suwarrow's interaction created structural asymmetries in the envelope, those asymmetries will appear as deviations from spherical symmetry in the expanding material, showing up as asymmetric absorption line profiles in the spectra. One side of the ejector moving toward us faster than the other, emission features stronger in some velocity channels than others, the spectral fingerprint of a star that was not alone when it died. Future papers will spend decades unpacking what those first hours of spectroscopic data contain. As for Suwarrow itself, the companion that triggered this chain of events, the object that plunged through Betelgeuse's chromosphere on every orbit for potentially millions of years, that drove the mass loss we could not account for, that left the wake Hubble detected in January 2026. The explosion is a catastrophic personal event. The shockwave will reach Suwa before the main body of ejecta does, bathing it in an intense pulse of X-rays and ultraviolet radiation that will strip material from its surface and deposit enormous energy into whatever atmosphere it has. When the ejector arrives, it will do more, stripping additional mass, pushing the companion, imparting a velocity kick that, if the explosion is asymmetric as most core collapse supernovae are, could be dramatic. Siwara may be flung outward on a hyperbolic trajectory, becoming a runaway star, a fast-moving object leaving the scene of the explosion at speeds that will be detectable and traceable for millions of years. Future astronomers studying the Betelgeuse remnant, in a distant enough future that the remnant has expanded to a scale where its internal kinematics can be mapped, may find a single anomalously fast-moving star fleeing the center, and from its trajectory reconstruct the story of what it was before the explosion. The companion that lived inside a red supergiant, the object that changed the timeline. The first 24 hours will also be something that no astrophysics textbook can fully prepare you for, because it will be a sociological event on a scale that has no modern precedent. Every streaming platform will carry live telescope feeds. Every major science account will be posting images as fast as the data processes. The single image of Orion with a blazing new point of light where the left shoulder used to be a modest orange star will circulate faster and more widely than any astronomical image in history. Governments will issue communications, schools will cancel their normal schedules, people who have never once deliberately looked at a star in their lives will be standing in their driveways looking up, because someone told them to, because there is something up there that has not been there before and will not be there in the same way again. The explosion will be the most watched moment in the history of stargazing, and what follows it will be permanent. Go on. Part 12. The Aftermath. A permanently changed sky. The peak will come, and it will not leave quickly. This is one of the things about supernovae that tends to surprise people who have not thought carefully about the physics. The assumption that an explosion is a brief event, a flash, something that arrives and departs. A supernova is not that. It is a months-long transformation, a slow and structured unwinding of a star's entire accumulated mass, and the light it produces during that unwinding follows a curve that has its own internal logic, its own pacing, its own phases. The explosion itself is instantaneous in the sense that core collapse happens in less than a second, but the light show that follows is measured in seasons. After the initial brightening driven by the explosion's raw energy and the rapid outward expansion of the fireball, the supernova transitions into a phase governed by something quieter and more patient, radioactive decay. The explosion synthesized enormous quantities of nickel-56, a radioactive isotope produced in the extreme temperatures and pressures of the core collapse and the shock-heated inner ejecta. Nickel-56 is unstable. It decays to cobalt-56, releasing gamma rays in the process. Cobalt-56 is also unstable. It decays to iron-56, stable, inert, the final product, releasing more gamma rays. These gamma rays, produced deep inside the expanding ejecta, do not escape directly. They are absorbed by the surrounding material, thermalized and re-radiated as lower energy light that gradually works its way outward and eventually emerges as the glow you see from the outside. This is the radioactive decay tail, and it is what keeps a supernova luminous for months after the initial fireball has faded. The brightness follows the decay curve of cobalt-56, which has a half-life of approximately 77 days. Slow, steady, persistent. For Betelgeuse, this sustained phase will keep the supernova visible as a naked-eye object for the better part of a year. The decline from peak will be gradual enough that casual observers checking the sky week by week will notice the slow dimming but will not see it happen in real time. It will feel like the way daylight shortens in autumn. You know it is happening, you can measure it, but you cannot watch it in the moment. Throughout this period, the supernova will be a fixture of the night sky in a way that no transient astronomical event has been in modern times. It will be there every clear night, in the shoulder of Orion, changing slowly, the most watched object in the sky by an enormous margin. The science unfolding during these months will be extraordinary in its depth and novelty. As the ejecta expands and thins, the layers of the star are progressively exposed, not all at once, but sequentially, from the outside in. The outermost layers are hydrogen, the star's original envelope, or what remained of it after Siwaha's years of orbital interaction, stripped material away. In the first weeks, the spectrum of the supernova will be dominated by hydrogen features, the characteristic signatures of a Type II supernova, the explosion of a star that retained its hydrogen envelope to the end. As weeks become months and the ejecta thins further, the spectroscopic window opens onto deeper layers. Helium, carbon and oxygen from the helium-burning shell, neon and magnesium from deeper still, silicon and sulfur from the silicon-burning shell that operated in the star's final years, and eventually at the center of it all the iron group elements, nickel, cobalt, iron, the products of the most extreme nuclear burning and the collapse itself. Astronomers following this spectral evolution will be doing something that has never been possible before at this level of detail, watching the internal structure of a massive star revealed in real time, layer by layer, as the explosion excavates it. Every model of red supergiant internal structure, the onion shell burning layers, the chemical abundances at each depth, the mixing that occurs during the explosion, makes predictions about what the spectrum should look like at each phase of this evolution. Betelgeuse will test every one of those predictions simultaneously, with a signal-to-noise ratio that dwarfs anything achievable for a more distant supernova. Papers will be written about this data for decades. The spectral time series from the Betelgeuse supernova will be a reference dataset for stellar physics in the same way that certain laboratory measurements are reference datasets in atomic physics, definitive, highly precise, and consulted by every subsequent generation. Months after the explosion, as the ejecta continues to expand outward and its density drops, it will begin to encounter the circumstellar material, the shells and arcs and filaments of gas that Betelgeuse has been ejecting for thousands of years through its stellar wind and its episodic mass loss events. These shells, whose discrete layered structure we discussed as evidence of Betelgeuse's non-steady mass loss history, have been sitting out there in space, slowly expanding at the much lower speeds of a stellar wind. The ejecta from the explosion is moving orders of magnitude faster. When the fast-moving ejecta collides with the slower-moving shells, it drives shock waves into them. Those shock waves heat the shell material, which then radiates, first in X-rays and radio waves as the interaction begins, then increasingly in optical emission, as the shock wave strengthens and more material is swept up. This circumstellar interaction will brighten the supernova remnant on timescales of months to years after the peak, producing secondary maxima in the light curve that encode information about the structure of the shells, their density, their chemical composition, their distance from the explosion center. Each shell that the ejecta encounters is a record of a past mass loss event, and the shock wave that lights it up is reading that record aloud. This circumstellar interaction phase is the beginning of something that will last not years, but millennia. The supernova remnant phase, the long, slow expansion of the ejecta through the surrounding medium, will produce one of the most structurally complex and visually spectacular nebulae in the Milky Way. In the first decades, it will be compact, bright in radio and X-rays, gradually developing structure as the interaction with different circumstellar shells creates rings and asymmetries. Over centuries, as the ejecta expands to scales of light years, it will develop the filamentary, bubble-like morphology that we see in mature supernova remnants like the Cygnus Loop or Cassiopeia A. Over thousands of years, it will grow to dominate a significant patch of the sky, visible in long exposure images as a complex web of glowing gas, oxygen, sulfur, hydrogen, all the elements that Betelgeuse synthesized and ejected over its 10 million year lifetime, now return to the interstellar medium to seed the next generation of stars and planets. At the center of this expanding nebula, if the standard models are correct, there will be a neutron star. Betelgeuse's mass, somewhere in the range of 16 to 19 solar masses, depending on which measurement you trust, puts it in the range where core collapse supernovae typically leave neutron stars rather than black holes, though the boundary is not sharp and the uncertainty is genuine. A neutron star formed in this explosion will be a sphere of matter roughly 20 kilometers across, more massive than the Sun, spinning rapidly from the angular momentum inherited from the collapsing core. If it produces beamed radio emission aligned favorably with Earth, and many do, it will be detectable as a pulsar within days or weeks of the explosion, its regular pulses of radio waves arriving at our antennas with a precision that rivals atomic clocks. If it is surrounded by dense nebular material in the early phase, and the radio beams are not aligned with us, it may instead appear as a compact X-ray source embedded in the center of the expanding remnant. A pulsar wind nebula, glowing in X-rays as the neutron star's rotational energy is converted into particle acceleration and radiation. Either way, the neutron star will be studied with an intensity that no neutron star has ever received. It will be close enough that the instruments of the next several decades, whatever those instruments turn out to be, will be able to resolve its properties in ways that are currently not possible for any neutron star in our galaxy. The physics of matter at nuclear density, the equation of state that determines whether a given mass of cold matter forms a neutron star or collapses further to a black hole, the mechanism by which rapidly rotating neutron stars generate their beamed radiation, all of these are open questions in fundamental physics, and the Betelgeuse remnant will bear on all of them simultaneously. And then there is the sky, the permanent, irreversible, quietly devastating change to the sky. For anyone alive to see Orion in the years after the explosion, the constellation will be wrong. Not wrong in a way that requires a chart to notice. Wrong in the way that a familiar face is wrong when something has changed. Immediately, instinctively apparent to anyone who has ever looked up at the winter sky and found that particular pattern of stars. The left shoulder will be empty, not dimmed, not reddened, not variable, empty. The orange-red point that anchored the upper left of Orion for the entirety of recorded human history, that appeared in Sumerian star catalogues, in ancient Egyptian astronomical texts, in indigenous navigational traditions on every inhabited continent, in every photograph of the winter sky ever taken, will simply not be there. Children who grow up after the explosion will learn a different Orion. They will look at historical photographs of the constellation and find them slightly strange, the way we find photographs of cities before major buildings were constructed slightly strange, recognizable but off, missing something that feels like it should have always been there. Star charts will be reprinted. Constellation guides will carry footnotes. The image of Orion that was reproduced on spacecraft, on scientific instruments, on the covers of countless books and magazines and educational materials, that image will become a historical artifact, a record of a sky that no longer exists. In its place, over centuries and then millennia, the nebula will grow. In the first decades, it will be too small and too embedded in its own bright emission to show structure to the naked eye. Over centuries, it will expand to a scale where long exposure images reveal its morphology. Rings, filaments, the complex wrinkled surface of an expanding shock encountering uneven circumstellar material. Over thousands of years, it will become a genuine spectacle in astronomical imagery, a nebula that future observers with their future instruments will study and photograph and use as a teaching example of how massive stars end their lives and return their material to the galaxy. It will outlast every human institution currently in existence. It will outlast every language currently spoken. It will still be expanding, still radiating, still carrying the chemical legacy of Betelgeuse's 10 million years of nuclear burning outward into the interstellar medium, long after everything we have built and written and recorded has dissolved back into the planet that made us. That is the ending of this story. But here is the thing about this particular story. It does not feel like an ending. It feels like a realization. The textbook said 100,000 years. The textbook was wrong. The companion was real. The interaction was real. The Hubble result was real. And somewhere between the 1400s, when the light we observe tonight left the star, and this exact second, the system has continued to evolve in ways we cannot see and cannot know. The present state of Betelgeuse is invisible to us. The future of Betelgeuse is uncertain in a way it was not supposed to be, and the only thing travelling toward us right now that could change that, the only signal that bypasses the light travel delay and announces the final event before the photons arrive, is a flood of neutrinos that no human sense can detect, waiting to light up a network of detectors buried under kilometers of rock and ice. We cannot know what is happening there tonight. We can only keep watching the old light and waiting.